Hello, everybody. We are in 5.7, complex zeros, which is basically the same as 5.6. Everything we've done in 5.6, we're going to do in 5.7. But 5.7 is about finding, well, 5.6 was about finding real zeros. 5.7 is about finding complex zeros. So right now we have a whole page of definition that I can read off. So a variable in a complex number system is referred to as a complex variable. A complex polynomial function of degree n is a function of the form. And once again, we see that really complicated looking function form. But remember, it just means highest power to lowest power to constant, right? Leading term, and with your constant in descending order. Okay. Where a sub n minus 1, a sub 1, and a sub 0 are complex numbers, and the leading coefficient a sub n cannot be 0. N is a non-negative integer, and x is a complex variable. As before, a sub n is called the leading coefficient of f. A complex number r is called a complex zero of f if f of r equals 0. Now, what does all that mean? Well, we are going to, like I said, solve for complex zeros today. And given an even degree function or an odd degree function, sometimes we will end up with a complex zero when you solve for x. So all we're saying here is that no matter if you have a real zero or a complex zero, and you plug it into the function, if it is a correct zero of the function, then you should always get 0. Because zeros of a function, when plugged in, make the function 0, right? But once again, today we're just looking for complex zeros. And we'll find real zeros as well, but it's all about complex zeros today. So we have learned that some quadratic equations have complex solutions. They'll have imaginary numbers. But that in a complex number system, every quadratic equation has a solution, either real or complex. This was proved by this really old dude named Carl Gauss. And he proved this when he was 22 years old. If you want to read some good material, Google this guy's name and look at all the stuff that he has proved. This guy was solving theories, making proofs since he was probably in elementary school. So really good read. Look it up. Let's see. So yeah, good stuff. He's the reason we're able to do this. So thank him, right? I mean, I'm pretty sure we're getting the simpler version of it. This is just college algebra, which leads us into the fundamental theorem of algebra, the thing that Mr. Gauss has proved. Every complex polynomial function f of degree n greater than or equal to 1 has at least one complex zero. And whenever we say complex, remember we can say an imaginary or even a radical. So if my 0 was the square root of 5, that is a complex number. Or even if it was 2i, which is imaginary, these are still considered complex numbers. Okay, and we have seen in 5.6 that yes, sometimes you will get a complex number or you will get an imaginary number. Okay, every complex polynomial function f degree n greater than or equal to 1 can be factored into n linear factors of the form f of x equals a sub n times x minus r1, x minus r2, all the way till you get to the final factor. So we've seen this and we've actually done this. What this theorem is saying is everything we've done in 5.6. We've taken a 4-term, 5-term, 6-term, 7-term polynomial and have factored it into smaller linear factors. So that's what we're going to do today. Again, like I said, nothing's different. Okay, so like I said, we're going to do everything in 5.6. We take these n amount of term polynomials, use P over Q, synthetic division, break them down, and for these problems, we'll most likely get a complex zero. Okay. Oh, what else? We can use the fundamental theorem of algebra to obtain valuable information about the complex zeros of polynomial functions whose coefficients are real numbers. Now we get into something called conjugate pairs theorem. We've seen the conjugate before. It's how you rationalize a denominator, a expression with a radical in the denominator. We multiply by the conjugate, right? Okay, so this says let f of x be a polynomial function whose coefficients are real numbers. If r equals a plus bi is 0, then it has a conjugate pair of a minus bi. So if a plus bi is 0, then a minus bi is a 0. Or the other way around. If a minus bi is a 0, this means that a plus bi is a 0. So it will always have a conjugate pair. This also goes for if I had a plus the square root of b, then it would have a conjugate pair of a minus the square root of b. So this is all conjugate pairs theorem says. If you have a complex 0, then you already know what the other 0 is because it has a pair. Okay. Corollary, a small proof or theorem, I think small theorem. A polynomial function f of odd degree with real coefficients has at least one real 0. So if we're given an odd degree polynomial, it says that we'll have at least one real 0 and the rest will be complex. And we've seen that before. Okay. So next we are just using the conjugate pairs theorem. So we're going to be given the degree of a function of a polynomial function, and we must use conjugate pairs to find the other zeros. That's all we're doing here, nothing else. So a polynomial function f of degree 5, whose coefficients are real numbers, has the zeros 1, 5i, and 1 plus i. Find the remaining zeros. Okay. So if we have a degree of 5, this means we should have 5 zeros. So with that being said, I'll put that there. Degree is 5. And zeros given are 1. That's not complex, that's a real number, so it won't have a conjugate pair. But the next 0 given is 5i, and 5i is complex, which means it will have a conjugate of negative 5i. And then the other 0 given is 1 plus i, and it will have a conjugate pair of 1 minus i. And that's it. There's our zeros. 1, 2, 3, 4, 5. Just like it says. Degree 5, 5 zeros, which is odd. And it just shows that we have one real 0 and the rest are complex. Okay, that's how conjugate pairs theorem work. And it will help us out later on when we start using synthetic division to break the polynomials down. Okay. A polynomial function of degree 4, whose coefficients are real numbers, has the zeros I and 1 plus I. Okay. So degree is 4, which means we should have 4 zeros. The first 0 given is I, which means that's complex, so it's going to have a conjugate pair of negative I. And then the other 0 given is 1 plus I, which will have a conjugate pair, because that's complex, of 1 minus I. There you go. That's it. Nothing to it. That's all we're doing. We're practicing using conjugate pairs there. Okay. And then a polynomial function of degree 6, whose coefficients are real numbers, has the zeros 2, 2 plus I, negative 3 minus I, and 0. Find the remaining zeros. Degree is 6. Put zeros. I'll put the real ones first. They give us 2, and they give us 0. Those are real numbers, so they're not going to have a conjugate pair. But then the first complex 0 they give us is 2 plus I. This is complex, so its conjugate is going to be 2 minus I. And then the last complex zero they give us is -3 minus I, and its conjugate will be -3 plus I. And that's it. 1, 2, 3, 4, 5, 6 zeros. 4 are imaginary, 2 are real. Okay, that's it. That's how conjugate pairs theorem works. All right. So if you're ever given a complex zero, you know you'll have a conjugate pair that follows along with it. So that kind of makes our work easy, if we're given that zero already. Right. Find a polynomial function with specified zeros. So for these examples, we're going to be given the zeros of a polynomial function, and we have to work backwards to build them into the actual function. So we have to build the polynomial given the zeros and work back upwards. All right, I'll show you what I mean. Find a polynomial function of degree 4 whose coefficients are real numbers that has the zeros 1, 1, and -4 plus I. Okay, so first thing we should do is always list the degree. The degree is 4, which means we should have 4 zeros. Here we are given the zeros, 1, 1, and -4 plus I. This is our complex zero, which means it's going to have a conjugate pair of -4 minus I. And there we go. 1, 2, 3, 4 zeros. Okay. Now what I mean is, what we have to do is, given the zeros, we have to put them back into factored form. And after we put them back into factored form, we must distribute and build the actual polynomial function. So remember that first, our zeros are given by x equals 1, x equals 1, x equals -4 plus I, and x equals -4 minus I. Okay, so when I say work backwards, I mean for x equals 1, take that 1 and move it back to the left. So you'd have x minus 1. And then for x equals 1 again, you'll have x minus 1. And then for this guy, you want to move both terms over, which means you're going to get x plus 4 minus I. And then for this guy, move both terms over as well, and you'll have x plus 4 plus I. So that's taking the given zeros, work it backwards, put them into factored form, and now we distribute. So the first ones are easy to distribute. These x minus 1s, we're going to FOIL those. Okay. So this is going to give us, once you FOIL these, you're going to get x squared minus 2x plus 1. Now for these two, we're going to FOIL these, but before we FOIL these, we need to put them in FOIL, what can you say? I'll say foiling format. So what we're going to do is take this x plus 4 and put parentheses around it to make it its own term. Same thing over here. This x plus 4, put parentheses around it to make it its own term. This is just going to make the distributing process easier, because if we didn't put x plus 4 as its own term and decided to distribute everything, which you may like, you can be like, all right, x times this, x times this, x times this. And then 4 times that, 4 times that, 4 times that. And then I times that, I times that, I times that. So you're going to have to distribute everything out. But if we group the x plus 4s together, it actually makes the distributing a lot easier to look at. Because now, since x plus 4 is its own term, because all we have to do is put parentheses around it, we can now FOIL it because we can consider that there are only 2 terms inside my parentheses. So this means that this x plus 4 will multiply that x plus 4. So what we're going to get down below, I'm going to put a bracket to be neat, is x plus 4 times x plus 4. And then do x plus 4 times positive I, which means you'll get I times x plus 4. And then now, take this negative I and multiply by the x plus 4, and that'll give you negative I times x plus 4. And then take this negative I times that I, and that'll give you negative I squared. Close bracket. Okay, trust me, this is a lot better than doing the distribution 3 times each for all 3 terms. Foiling this is going to be a lot easier. Okay, so now, all we have to do is clean up inside the brackets. So this will stay the same, but now we FOIL these 2, which will become x squared plus 8x plus 16. And then we notice that this ix plus 4 and this negative ix plus 4, they are the same exact term. One's positive, one's negative. They will cancel. Gone, gone. And then, if you guys remember this, I'll write this over here, or maybe I can't. I'll write it at the top. So, quick little refresher, right? Remember that I is the square root of negative 1. I squared is just negative 1. So this is something we should know, or maybe just refresh you on it, right? So this means that this I squared becomes negative 1. But watch out for that negative waiting on the outside. So I'll write it in though. You're going to get minus negative 1, close bracket. Okay. And then you get x squared minus 2x plus 1. And once you clean everything up, this should give you x squared plus 8x plus 17. Right? Plus, plus. Yep. And then before I continue forward, let me actually check what my MATLAB wants. So give me one moment. I'll look this up. Let's see. We're here. And then, let me see. I don't know if it wants us to FOIL the whole thing out. Preview. Yeah, okay. So yes, it wants us to FOIL everything out. Distribute everything everything out. Okay, just had to double check that. Okay, so now all we have to do is distribute more. Okay, so now we're going to distribute these three-term polynomials with each other. So this x to that x, we get x to the fourth, eight x cubed, and 17x squared. Then do it again for the 2x. Negative 2x cubed minus 16x squared minus 34x. All right. And then do it one more time for the 1. Plus x squared plus 8x and plus 17. Okay. Everything has been distributed out. Now we must combine like terms. Start with the highest power first. And this is how my MATLAB wants the answer, since I just looked it up. It's going to be f of x equals a. It puts the a there for you. And then we'll bring the x to the fourth down. That's the only x to the fourth in here. And then we'll go over to our cubes, 8x cubed and negative 2x cubed. So I'll get 6x cubed. And then I'll go to my squares, 17x squared, 16x squared, and x squared. That's going to give me 1x squared, 2x squared. And then last, well not last, is my x's, negative 34 and 8. That's going to give me negative 26x. And then last that's left over is my constant of 17. Close parentheses, and there is our answer. Okay. Hey, that wasn't too bad, right? So once again, this exercise was get the zeros. And if you're given a complex one, make sure you list the conjugate pair one. Then put them into factored form, and then distribute everything. Distribute, 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 distribute till they get to the very end, and there it is. This is the polynomial that gave us those zeros. And I guess they put an a in front because we don't know what the leading coefficient is. Sure. All right. Well, that's it. So fun process. All right. Small theorem. Every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. So once again, this theorem is stating everything we've done so far. We have taken a polynomial function with real coefficients, and by P over Q's, by rational zero theorem and synthetic division, we can break it down into linear factors. So they just keep stating everything we know already. We know this, right? For this problem, we want to find the complex zeros of the polynomial function. So basically, we're going to find the potential rational zeros, throw them into synthetic division, and keep breaking it down and find the real zeros and also find the complex zeros. Okay, so first up is the degree, which tells us how many zeros we have. So we have a degree of 4, which means we should have 4 zeros at the end, real and complex together. Now for our potential zeros, let's go with that. P belongs to the constant, which is 18 or negative 18, doesn't matter. and find all the factors of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 18. And then Q gives me 3, and plus or minus 1 and 3. Okay, then you put P over Q. And plus or minus, and take all your factors of P, put them over Q. So we'll get 1, 2, 3, 6, 9, 18. And then put them all over 3. So you'll get 1/3, 2/3, 3/3 we have, 6/3 we have, 9/3 we have, 8/3 we have. So those are our potential zeros, and we have, oops, we have 1, 2, 3, 4, 5, 6, 7, 8, 16 tries to get it right. Okay, so let's go ahead and set up for synthetic. All right, and all powers are accounted for, 4, 3, 2, 1, 0. So 3, 5, 25, 45, negative 18. First number comes down, and should we try 1? Let's see. If I try 1, you'll get 3, 8, 8, 33, 33. That's going to be too big. So 1's not going to work. -1, we could try. If we go -1, you'll get -3, 2, -2, 23, -23, and 45 from 23 is what? 22. So that's not going to work out for us. So 1 and -1 are out. So let's go 2. And for this one, since this is positive, 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 I think we should start by choosing negative numbers. So let's try -2. So you'll get -6, -1, and then you'll get 2, you'll get 27. And then -2 and 27 is -54. And 45 plus -54 is a -9. And then you get 18, which gives me 0. Okay. So we have successfully broken it down once. So rewrite in depressed form. X plus 2, and the highest power was to the 4th. So we broke it down. So we're going to get 3x cubed minus x squared plus 27x minus 9. Okay. And then we can throw this polynomial back into synthetic division, or we can try to factor it. So before we do synthetic division again, let's see if it factors by grouping. If it doesn't, more synthetic division. Put those together, and you get x plus 2. Take an x squared out, you get 3x minus 1. Over here, take a 9 out, and you get 3x minus 1. Hey, and grouping worked. So these 3x minus 1s are the same. Take those out. And all that's left over is that x squared plus 9. Okay. Here is the factored form of the equation above. Now all we have to do is find the zeros. So this would be f of x equals, we have found the zeros, and the first two are given. X equals -2, x equals 1/3. The next one, we have a little bit of work to do. X squared plus 9 equal to 0. X squared equals -9. Square root. And x equals, the square root of -9 is going to be plus or minus 3i. And there it is. I guess if my math lab wants its answer for the zeros, you'll have -2, 1/3, positive 3i, and negative 3i. There we go. And once again, we have 4 zeros, and the degree was 4. So 2 of them were real, 2 of them were imaginary. And that's what we're looking for today, are the complex zeros. So actually, maybe if you just wanted a complex, you would just put 3i, and -3i is your answer. Okay. And I think, yeah, we're on the last one. So once again, I only showed one example because this is everything we've been doing so far. So no need to show another example. Find the rational zeros, break it down by synthetic division. If you can't factor it by grouping, then break it down by synthetic division again until you can factor it. Once you have completely factored it, set them equal to 0, set your factors equal to 0, your linear factors, and then solve for x. Okay. Last one. This one's fun. Mind-blowing at that. Test the given zero by synthetic division to find the remaining zeros of the function. F of x equals 2x to the 4th plus 5x cubed plus 5x squared plus 20x minus 12. So we want to test the given zero of -2i. And they're giving us a complex zero, which means we know the other zero already by conjugate pairs. If we're given -2i, then we already know the other zero is positive 2i. So let's go ahead and try imaginary numbers in synthetic division, or try a complex number in synthetic division. It's going to be a great time, don't worry. So we'll start with -2i. And all powers are accounted for. 4, 3, 2, 1, 0. Okay. 2, 5, 5, 20, -12. First number comes down. Okay. So it's gonna get messy. -2i times 2 is -4i. 5 plus -4i is going to end up being 5 minus 4i. Okay, so we're going to need a little side work section here, because now it's -2 times 5 minus 4i. Distribute the -2i, and you're going to get -10i plus 8i squared. Well, remember, I squared is -1. So this becomes -10i minus 8, which is going to go right underneath the next 5. So let me see if I can actually write smaller. So this is going to be -10i minus 8. Okay. And then add those together, which I said lots of side work, right? So now you have 5 plus negative 10i minus 8, which is just 5 minus 10i minus 8, which becomes, actually, let me write it that way. Negative 3 minus 10i. So that's what's down here. Negative 3 minus 10i. Okay. Maybe I should put some dividers in here. Okay. And now we multiply negative 3 minus 10i by negative 2i. So negative 2i times negative 3 minus 10i. So you're going to get 6i plus 20i squared, which becomes 6i minus 20. So that goes right underneath the 20. And now you'll have 20 plus 6i minus 20, which is 20 plus 6i minus 20, which gives you 6i. So your 20s cancel, and we're left with 6i. Okay, last one. Negative 2i times 6i gives me negative 12i squared. And I squared is negative 1, so we get positive 12. So this will give me 12, which, look at this, you get a remainder of 0. Amazing, right? But we're not done, because we have to break it down one more time. We are not going to write this in depressed form. That'll be way too depressing. We're just going to throw our quotient back into synthetic division. So all of this, we go back into synthetic. And you're going to have 2, 5 minus 4i, negative 3 minus 10i, and 6i. And since the first complex zero we used was negative 2i, the next complex zero we're going to use is 2i. All right, now don't worry. This one's going to work out a lot nicer than the one above it. The 2 comes down, and then 2i times 2 is 4i. The 4i's cancel. You get 5. 2i times 5, 10i. Your 10i's cancel. You get negative 3. 2i times negative 3, negative 6i. Remainder 0. So nice. Okay, now we know that we have zeros, negative 2i and 2i. We have to find the remaining zeros. So all we have to do is take this quotient and put it back into polynomial form. So we just broke it down twice, which means if the power was x to the 4th, if we broke it down twice, the power is now x squared. So what we have now is 2x squared plus 5x minus 3. And now, hopefully, this factors. If it doesn't, we got some more work to do. But since they already gave us 2 complicated zeros, this should always factor. Should. If it doesn't, I'm sorry for picking a hard problem for you. Okay, so this should factor to 2x, I think, plus a number, and x minus a number. And the only factors we're looking for are 3. So I think 3 should go here, and 1 here. But if I FOIL this, I get 2x squared minus 6x plus x, which will give me negative 5x. We're looking for positive 5x. So all you have to do is switch the signs. Make that plus 3. And that'll fix it. And we have successfully factored it, which lets us find the remaining zeros, which are x equals 1/2 and x equals negative 3. Okay. So it said find the remaining zeros. So a good MyMathLab answer would be negative 2i, 2i, 1/2, and negative 3. I mean, it probably only wants these 3, but I'm just listing all the zeros together. All right, and that's how complex numbers work in synthetic division. It's oh so magical. I love it. And that is it for 5.7. I hope you enjoyed all of that, except for reading that whole first page. I'm sorry for all my, it probably looks like the video is like choppy. It's because I kept getting, not interrupted. I would interrupted to mean to say. I got busy doing other things. But video is done. Enjoy. See you the next one.